In this lecture, I'm going to introduce you to the concept of entropy. It's a phenomenally important concept. It'll be absolutely vital because the second law of thermodynamics, which we'll talk about in the next lecture, will be based entirely upon entropy itself. Of course, we're going to talk about entropy in terms of thermodynamics, but then the real understanding comes from statistical mechanics, which came much later. But the really interesting thing is that entropy is a concept that has gone now across many different fields. So, for example, information theory, how fast, how much information can travel over the internet, determined by something called Shannon entropy. Even economists deal with the concept of entropy. What it is, we will encounter, but slowly and with pictures in the beginning. Let's start by understanding entropy in a qualitative way. By qualitative, I mean without using formulae or mathematics. We'll come to that later. Okay, so here is a container with some molecules that are confined by this partition to the left-hand part of this box. So each molecule can move around freely, but only in this part. When I remove this partition, then each molecule has a bigger volume in which it can move. So, although there was uncertainty about, let's say, where this molecule was, it could have been here or here or here or here or here, but now there's much more uncertainty because it can be here or here or here or here or in many different places. So we've gone from a situation of low uncertainty to a situation of high uncertainty. Take this. Here there's some kind of a crystal, let's say sodium chloride. Every atom is bound to every other atom through bonds, and this has made a stable structure that of a crystal. Now, if this crystal is put inside some solvent over here, let's say water or paraffin or alcohol or whatever, then these bonds break. And so each atom or molecule has got much more space in which to move around with. So the uncertainty here, which was fairly low, has now become much greater. Again, we've gone from a low uncertainty situation to a high uncertainty situation. Here's what chemists call osmosis. And again, entropy is involved over here. So here is some solvent, the blue liquid over here, call it water. And in that solvent is a solute. So again, this blue could be water and this could be salt. Now, here are the solute molecules. And now we put over here what is called a semi-permeable membrane, which means that water or that solvent can move across, but it prevents the solute molecules, let's say sodium chloride, from going from left to right. So what happens is that the water travels from left to right, but the solute molecules are stopped. And so after some time, we see that the concentration here and the concentration here become equal. Again, this is a situation where the net uncertainty has increased. Well, now it's time to get a little more precise. What is entropy, after all? Let me list the main points. First, it is something that increases with time. You could see that very easily here and here. In other words, if you were to make a video of this situation or this situation or this situation, you would immediately know whether the video is being run forward or backward. So when a system's entropy increases, you know that time has passed in the forward direction. Next, entropy has something to do with the spread of matter and energy. Now you should not be too surprised because Einstein told you that matter and energy are in a sense interchangeable with each other. However, we will get more precise on this when we come to actual formulas. And finally, I'd say that entropy is something that is related to microscopic motions, to disorder, to how atoms, molecules, quarks, nuclei, strings, yes, even superstrings, how they move around. That's disorder. But let me warn you that this so-called understanding that we have so far, very, very qualitative of entropy, comes from statistical mechanics, not from thermodynamics. That's not the way it emerged classically. It was only after a long struggle, lot of thinking, that we got to understand the relationship between the statistical mechanics understanding of entropy and that coming from thermodynamics. So then let's go back to the old definition, 1865. And this says that suppose I have a body. It has something called entropy and it's at some temperature T. If I add to this a small amount of heat, let's call that delta Q, and it's sufficiently small so that the temperature of this doesn't change. So whatever I put in, the small amount of heat, it will increase the entropy by a small amount delta S, but the temperature will remain unchanged. So this could be a huge body, and a small amount of heat is not going to change the temperature. However, the entropy is going to change by this amount. Now that's a definition, and it doesn't seem to have anything to do with atoms, molecules, or whatever. The only condition is that the heat must be added reversibly, which means that you can go from this situation to that situation or back, and this can be done if you do it slowly enough. So you could add a finite amount of heat in small steps. But let's take an example now where this doesn't have to be some huge body. Okay, so here is a block of ice, or a small piece of ice or whatever. Now ice, as you know, melts, and while melting, it will keep its temperature at 0 degrees centigrade or 273 degrees Kelvin, and that temperature will be maintained until it melts away totally. So let's apply this formula here. As this block of ice acquires heat delta Q, its temperature remains constant, 273, so that's the change in entropy that's happening. You see, already you can understand there's some sort of connection because the entropy has increased. The water molecules which were confined to this block of ice now are allowed to spread out. They've become liquid, and the liquid is now in drops. So the entropy is increasing. You can actually go out and measure the amount of entropy that has actually increased by this definition. And you will find that for 1 mole of water or ice, you need to add 6,008 joules in order to melt it. And so the specific entropy for ice is 22 joules per degree Kelvin for 1 mole. In terms of a microscopic picture, here's how we understand it. Here's ice. The ice has all these bonds. It's in a hexagonal structure, very stable. Now, when you add heat, these bonds start breaking. Not all of them. There are still bonds, hydrogen bonds, that are keeping the water molecules together. However, there are fewer of them. So whereas you had a very ordered system over here, which means small entropy system here, now you have a system with larger entropy, larger uncertainty. So you see, at least we are making some kind of connection here. We are adding heat, we are increasing the entropy. As I stressed earlier, this delta Q has to be very, very small, and so delta S is very, very small. They're infinitesimal quantities. But what if you have a finite amount of heat delivered to any system? So take, for example, this gas. We could take anything, but this gas is defined by a number of state variables. So there's the pressure, the volume, the temperature, the number of molecules. And now when I remove the partition and we have this situation, there'll be a different pressure, volume, maybe temperature, and the number of particles. Well, the number of particles is the same in this case, but there could have been a leak, in which case Na could have been different from Nb. Close your eyes now and imagine a situation where you have a lot of axes. So this is the P axis, this is the V axis, there's an axis which I haven't drawn, which is the T, temperature axis, and there is the number n, which would take us into 4 dimensions, which we can't really draw. But in principle, we have P, V, T, N, and if it's another system, let's say a magnetic system or a more complicated system, then we could have a lot of these over here, maybe 5, maybe 10, maybe 20. This is a point A in thermodynamic space. And this is another point B in that same space. Now, there are various paths that can connect A to B. So I can change P, T, N, whatever, and go along one path. Or if I change them in a different way, I can go along this path and arrive again at the point B. If we want to calculate from here how much has been the total change in entropy, then that change of entropy can be got by taking delta S1, adding it to delta S2, delta S3, and so forth. So first I add delta Q1 and then wait, and then add delta Q2, wait, and so forth, so that all of this is done reversibly. When I say wait, that doesn't mean you have to wait forever. It only means that you have to wait for the system to come back into thermodynamic equilibrium, which is roughly the amount of time it takes for one molecule to collide with another molecule. And so that's to be measured in microseconds or whatever. It's a very, very small time, the equilibration time. Now, if you add these all together, that's the same as doing the integral of this quantity from A to B. So we can go along this path, or we can go along this path. In both cases, we will have to do an integral. If one does things slowly so that we are in equilibrium at every point, then we can go on this path, do the integral, and get an answer. And I say that it can be proved, and hopefully in this course we will prove it, but not right now, that this integral actually just depends upon the endpoints. So this integral is the value of the entropy at B minus the starting entropy which is S at the point A. There's another way of saying this, namely that entropy is a state function. So here's what I wrote down before, that the integral from A to B is just S of B minus S of A, and we'll call this the difference in the entropies. So it only depends upon where you started from and where you ended at. And now here's something very, very interesting, because if the entropy only depends where you start from and where you end at, well, I could go by a reversible path from A to B, or I could go from A to B by some irreversible path. And what if I go from A to B and from B to C? Now you know from calculus that I have the integral from A to C being the same as the integral from A to B plus the integral from B to C. In other words, the integral from here to here is the same as the integral from here to here, and then the integral from here to here. That's provided that this path and this path are reversible. Okay, now let's see what that means mathematically. So this first integral is SB minus SA. The second integral is SC minus SB. So what's at the top minus what's at the bottom? Same here. Add them up. And of course, that's SC minus SA. This is very nice because look, if I take C equal to A, then these cancel. In other words, the integral around any closed loop in thermodynamic space is equal to 0. Or to be more precise, in a reversible loop, the integral of ds is 0. All this is a little abstract, so let's do a little calculation, and this will be an expansion of a gas at constant pressure. To do this integral, you have to know the path. Of course, the path has to be a reversible path. You have to go along it very, very slowly. So here is a gas whose temperature initially is TA. It was originally, the piston originally was here at this point and finally is here. The reason that the gas has expanded is that I've put it in contact with a large amount of matter. Let's call that a reservoir. So a reservoir is something that can contribute a lot of heat without changing its temperature at all. And so this reservoir, which is at temperature TB, is now in contact with this gas, which was initially at TA, and it has expanded from here to here, the pressure being constant. Now you know that if a gas expands at constant pressure, then if its temperature changes by dT, that's because you've added a small amount of heat delta Q to it. That means there's a specific heat, Cp, and the amount of heat that you had to add would be delta Q, which would be proportional to dt with this in front of it. Okay? So now let's do an integral. And this integral is of delta Q over T. This will be the increase in the entropy of the gas. So G over here is for gas. Instead of a delta Q, now put Cp dt. The gas, which was originally at temperature TA, will now be heated up to temperature TB. And so we've gone from temperature TA up to temperature TB. This integral is just log of TB minus log of TA, because dt over t integral is log of t, which is the same as log of TB over TA. Simple enough. Now, what is the change in entropy of the reservoir? Because the reservoir also has heat added to it, actually subtracted to it, so a negative addition. That means we have to get the change in entropy of the reservoir by adding up all the small amounts of heat that have been taken away from it. So this delta Q over here is essentially going to be negative divided by the temperature of the reservoir. But the temperature of the reservoir doesn't change, so we can take it outside the integral, and this dq integrated is the total amount of heat that has been lost by the reservoir. That heat has gone into heating up this gas. That's just the first law of thermodynamics, which says that energy is always conserved. Now, this total amount of heat that was lost was just the specific heat of the gas into the change of its temperature, and you can see that this is a negative quantity because TA is less than TB. It was a hot reservoir and a cold gas. Let's take the sum of this, delta S gas, and this, delta S reservoir. Well, I'm going to give this a fancy name. This will be called the change in entropy of the universe. That's because our universe consists just of the gas and the reservoir. If you add them up, well, then you just get this quantity over here, log of TB over TA minus 1 plus TA over TB. Now, this quantity, I claim, is always greater than or equal to 0. It'll be equal to 0 if TA and TB are the same, and that's pretty obvious because this will be 1 minus 1 and this will be log of 1. But what if TB is bigger than TA? Well, then you will show as an exercise that delta S is positive, and that's actually trivial. Just put x equal to TB over TA, put that over here, and what you have to show is that log of x is always greater than 1 minus 1 over x for x being positive. Let's ask what happens when a gas expands reversibly versus irreversibly. We'll calculate the entropy change. Now, here's 1 mole of ideal gas. It's at some temperature T, has some volume V, and we let this process happen slowly, reversibly, from here to here. We let the volume double. So T goes to 2V. And for this isothermal, reversible, which means slow expansion, we want to find the change in entropy of the gas and the universe. So look, it's isothermal, which means the temperature has not changed. We know how to do this, the work done by the gas, not on the gas, by the gas, is the pressure into the volume, pressure into the change of volume, and then you integrate this from the initial volume to the final volume, in other words, V to 2V. Now, PV is equal to RT. N is equal to 1. Remember, it's a 1 mole of ideal gas. So P is then RT. T we can take outside because T is constant, remember? And so we just have the integral of dV over V. So that's log of 2V minus log of V, which is log of 2. This is the work done by the gas on the piston during the expansion from here to here. Now, the first law of thermodynamics says that the change in the internal energy of the gas is equal to how much heat you have put in, and add to this how much work you have done on the gas. Here, delta W is the work done by the gas. Now, for an ideal gas, the energy of the gas depends only upon the temperature, and the temperature has not changed, so there's no change in the internal energy of the gas. We put that to 0, which means that delta Sg, the change in the entropy of the gas, is equal to the amount of heat that you've put in divided by the temperature of the gas. But delta Q then is exactly equal to delta W, but delta W we have calculated to be RT log 2. And so R log 2 is the change in entropy of the gas when it is allowed to expand reversibly, slowly, and of course at constant temperature. Now this gas did work, and so heat came from the outside, from the reservoir. So the reservoir here means that there'll be atmosphere out here. Maybe there's water, maybe this gas has been put into water or whatever. But now we must calculate the change in entropy of the reservoir. So the change in entropy of the reservoir is the amount of heat put into the reservoir divided by T. But actually it's not heat put in, it's heat taken out from the reservoir. The reservoir has given heat to the gas so that it could do the work and expand. With this minus delta Q over T, we get minus R log 2 for the reservoir, which means that the change in entropy of the universe. So here the universe is the reservoir and the gas. Of course, there's nothing else. There is no change in the entropy of the universe. Now, this is worth noting. The entropy of this gas has definitely increased. You can see that. There's more uncertainty over here. But in whatever constitutes the reservoir, the atoms or molecules in that, there's a corresponding decrease in the entropy. And the two exactly cancel each other. Zero change of entropy for the universe. What would happen? Ask yourself what would happen if you had 1 mole of ideal gas, exactly the same as above, and you were suddenly to remove this partition. If you suddenly remove it, then this gas expands instantly or in a very short time and fills this whole container. It does not do any work because there's no piston to push against. This is an irreversible process. You can never have this going back into this situation. So how does one calculate the entropy? After all, there's no integral to be done over here because that integral can only be done if it is a reversible process. Now again, delta U is delta Q minus delta W, the first law of thermodynamics. There is no change in the internal energy of the gas because the temperature is constant. It has not changed. In this case, there was no work done by the gas. There was no piston and so no work, which means that delta Q is 0. So no heat flowed in from the outside world, from the outside reservoir. In that case, delta Q is equal to 0. This means that the total change in entropy, now there's no heat flowing in from outside, so delta SR is 0. And so the total change of entropy, delta S, will simply be this, which is this, meaning R log 2. Is that a surprise? Not really, because we know that entropy is a state function. It doesn't matter how you got to this configuration over here. If you've calculated the change in entropy using a reversible process and arrived at T2V, then if you arrive at T2V by an irreversible process, the entropy change will be exactly the same. And so to conclude, whether you expand reversibly from this situation to this situation or go directly, instantly from this situation to this situation, in both cases the change in entropy of the gas will be exactly the same. However, the change in entropy of the universe will be different. Just a few minutes ago, we talked about thermodynamic space. Remember, that was an axis of pressure, volume, then there could be temperature, other things. We have some initial state, and if we get back to the final state, well, that is called a thermodynamic cycle. And cycles in thermodynamics are extremely important. We'll talk about them later. But here there is also the word reversible, and you know what that means. That means that at every point on this path, the system is in equilibrium. So you're doing it slowly. Of course, slowly doesn't mean very, very slowly. It just means that that time has to be bigger than the time between two collisions within the gas. And that's in microseconds. Again, to repeat, if you have A, which is a whole bunch of numbers that defines the thermodynamic state of the system, well, that A changes into B. If it changes slowly, then it's a reversible path from A to B. And this would be a closed cycle. So you go from A to B by some path, B to C, C to D, D to A. Now, in these reversible thermodynamic situations, no frictional forces are allowed. You could say that we deal with conservative systems. On each segment, let's say this, you could have something that is constant. Maybe the thing that is constant is the temperature, or maybe it is the pressure, or the volume, or the entropy, or the enthalpy, whatever. Or maybe nothing is constant on this. Remember that the only important thing is that the system be in equilibrium at every point along this path over here, or this path, or this path. We must remember that on every segment of this closed cycle, you can have heat being transferred in or out of the system. And of course, this is a cycle, which means that all state variables return to their original value. And so the same values of pressure, volume, temperature, number of atoms, etc., etc. Of course, you will do work, or work is done by the system by going around the cycle, because the pressure will have some non-zero value, and there will be change of volume. So P dV will be the small amount of work in going from, let's say, here to here, or from here to here. When we add up all those small amounts of work done, then we'll get the total work which is done by going around the cycle. And of course, because an expansion means that work is done by the system, P dV is positive. On the other hand, if the system is compressed, then you have done work on the system. In other words, reversing the direction reverses the work. So going around in one way and going around in the opposite way, they will have opposite signs for the work. Finally, let us work out an example of a thermodynamic cycle which has got 3 segments to it. We'll start from A, where the pressure is P1 and the volume is V1. From A, the system goes to B along an adiabat. Now, on the adiabat, or this adiabatic path, no heat is allowed to enter or leave the system. So delta Q will be 0. Then the system will go from volume V2 to volume V1 while keeping the pressure constant at P2. And finally, in going from C to A, the volume will be kept constant and the system will go from pressure P2 to pressure P1. We are asked the following. This ideal gas expands adiabatically from P1 V1 to P2 V2, that is to say from here to here, then compressed isobarically, which means at constant pressure, and finally the pressure is increased from here to here. Now we want the work done by the engine and the heat input. Let's look at the work done by the system, and that is PdV added up on all the segments, the first, the second, and the third. So let's see what these three integrals are: A to B, B to C, C to A. Okay, now it is perfectly clear that this third integral is 0 because there is no change in the volume. And so this dV is 0, and there's no change in the volume. In other words, C and A represent the same volumes. The second term here, PdV, has constant pressure, so just take P, whose value is P2, outside, and the integral is from here to here, V2 to V1, and this is obviously V1 minus V2, what's at the top minus what's at the bottom. The first term will need a little bit of calculation. You remember that in an earlier lecture, I derived that PV to the gamma is equal to a constant. Here gamma is the ratio of Cp to Cv. You can look back at the previous notes for that. Now in going from A to B, the volume has changed from V1 to V2. And so the integral is from V1 to V2, and now we need to write P in terms of V, which is easily done because P is then C over V to the gamma, which means that when you integrate it, you add 1 to the numerator and 1 to the denominator, and then this thing comes over here. So this integral is what you have here. Now this is easily simplified. We will simply substitute V from here. From here, V to the gamma is equal to C divided by P. And so this becomes much simpler. It's simply 1 over 1 minus gamma into P2 V2 minus P1 V1. And so just add this up. The work done is this P2 V1 minus V2 together with what's up over here. This is the total work done by the engine. As an exercise, I will leave this last part over here. Calculate the heat input. Obviously, there's no input from here, but you can calculate the heat that is put into the engine on this path and on this path. Good luck in that.